Moving forward, we now study the CNN named GoogLeNet, designed in 2014. The original paper is this one. You can look into it to find more details on this network. The aim here is to build a deeper and wider neural network while keeping the number of parameters small. This network is able to approximate more complex functions while being robust to overfitting and computationally appealing. The method to do so is simple. One-by-one convolutions are used before applying convolutions with larger filters, 3x3 or 5x5. By properly choosing the number of one-by-one filters, it helps reducing the overall number of parameters since it helps controlling the depth of the volumes taken as input by 3x3 or 5x5 filters. Value activation functions are used, and all feature maps of a given layer have the same spatial resolution. Here is a scheme of the inception model, which is at the heart of GoogLeNet. On the left, you have the naive version in which the idea is to create a layer composed of 1x1, 3x3, 5x5 convolutions and pooling. Such an inception module corresponds to a large number of parameters. Indeed, the number of parameters of one 5x5 convolution is equal to 5x5 the depth of the input volume, which can be really large. In order to reduce the number of parameters needed in this layer, you can add one-by-one convolutions before each filter in order to reduce the depth of the volume. Indeed, the depth of the volume output by p one-by-one convolutions is p. Choosing p small enough reduces drastically the number of parameters involved in the whole layer, since the next 3x3 or 5x5 convolutions are applied on a volume of depth p instead of the original depth. Note that you can apply the one-by-one convolution after the max pooling operation and not before, since there is no trainable parameters involved in the pooling operation and thus no need to reduce the depth of the volume before applying pooling. Here is a table displaying the number of parameters by layer in the network together with the characteristics of all layers. The parameter column is the penultimate. You can see that, contrary to previous networks, there is only one fully connected layer at the end of the network. Contrary to previous approaches, the convolutional layers are the layers containing the largest numbers of parameters. Remember that for the network we have seen so far, the vast majority of the parameters were found in the dense layers at the end of the network. Here is the architecture of GoogLeNet, which is difficult to read, so here is a zoom. The architecture starts on the bottom left, input layer, and ends on the top right, output layer, softmax 2. Note that you have also some layers called softmax 0 and softmax 1, which are auxiliary classifiers that are put in the middle of the network to help the optimization procedure. Indeed, as for classical neural networks, CNN may suffer from vanishing gradient phenomenon. In order to backpropagate the gradient, we can add some auxiliary classifiers connected to intermediate layers. During training, the loss of auxiliary classifiers is weighted, here by 0.3, added to the output loss of the network. This loss is used for training, which helps to detect how the early layers of the network impact the auxiliary classifiers. At inference time, auxiliary networks are just removed and the prediction is obtained via the output layer, softmax 2. Auxiliary classifiers helps the gradient flow to reach the first layers of the network. The auxiliary classifier networks are composed of averaging pooling, one-by-one convolution with ReLU, a fully connected layer with ReLU, a dropout layer, and a final linear layer with a softmax activation function. The weights are drawn from a Gaussian distribution and biases are set to 0. The optimization procedure used in the stochastic gradient descent with momentum with a batch size equal to 200. The learning rate is the same for all layers with the following heuristic. The learning rate is initialized at 0.01, and you multiply it by 0.96 every 8 epochs. The training lasts 125 epochs. In the first table, we have the performance of GoogLeNet compared to VGGNet and other algorithms. GoogLeNet improves slightly over VGGNet. The number of parameters in GoogLeNet is drastically reduced compared to AlexNet, 4 millions of parameters compared to 60 millions for AlexNet. The main idea to remember for GoogLeNet is the inception module, and the fact that you can use one-by-one convolutions to reduce the depth of volumes. For this network, note also that there is only one fully connected layer, which helps reducing the overall number of parameters.